Good day everyone. Our study, Development of Piezoelectric Charging Station for NU Nazareth Harnessing Foot Traffic for Sustainable Energy, explores how foot traffic can be converted into renewable energy using piezoelectric technology.
Of the background of the study. Piezoelectricity creates electricity from pressure or movement, making it a good option for clean energy. Since fossil fuels harm the environment, people are looking for better energy sources like this. However, there isn't much research on using it in busy places like schools. This study at NU Nazareth explores how piezoelectric energy can help make the campus more eco-friendly and use less fossil fuel.
For the purpose of the study, this study aimed to install a piezoelectric charging station at NU Nazareth School's fire escape mezzanine to promote sustainable energy and advance piezoelectric research. The station converted footstep energy into electricity using piezoelectric sensor tiles, providing students with a free phone charging option while reducing reliance on non-renewable resources. The initiative raised environmental awareness and encouraged further research on energy storage, efficiency, and scalability. For the research questions, first, what is the charging time of piezoelectric charging station in charging the Android and iOS phones of students at National University of Nazareth School? Second, what is the voltage output of the piezoelectric charging station under varying load conditions and how does it affect voltage stability? Third, what is the number of piezoelectric ceramics needed to have a working condition as a phone charger? For research hypothesis, according to the study's hypothesis, the National University of Nazareth's piezoelectric charging stations' performance and reliability are greatly affected by variables including the quantity of piezoelectric ceramics, load circumstances, and charging duration. It is anticipated that adding more ceramics will stabilize voltage output, lessen fluctuations, and improve charging dependability. The study intends to ascertain the ideal charging time for iOS and Android phone, the ideal number of ceramic for steady charging, and the effect of load conditions on voltage stability. Optimizing piezoelectric charging stations for students' safe, reliable, and effective charging is the aim.
This explains the mechanics and real-world impact of a piezoelectric charging station powered by foot traffic. It describes how walking generates mechanical energy, which is captured by piezoelectric sensors and converted into electrical energy. This energy is then stored in a battery or capacitor and regulated for efficient use. The implementation of this system focuses on user interaction and usability, ensuring it is simple and intuitive to use. Additionally, the sustainability impact is emphasized as the system provides a clean, reliable, and eco-friendly energy source that benefits both society and the environment.
Methodology.
This research utilized a convergent quantitative method to evaluate the technical viability and user interaction of a piezoelectricity-powered phone charging station at NU Nazareth School. By combining experiment and analysis, the efficiency, durability, and viability of the piezoelectricity charging station were assessed, indicating its potential as a sustainable energy solution.
Data analysis. The study involved testing the piezoelectric charging station under different conditions to measure its voltage output and efficiency. Researchers examined how factors like pressure, the number of ceramics, and load condition affected the station's ability to generate a stable and reliable power supply. Ethical consideration. The study ensured participants were fully informed about the research object and to voluntarily agreed to participate confidentially was maintained and steps were taken to disclose any funding sources or conflict or interest of full transparency and integrity research.
The data collection procedure for piezoelectric charging station. The steps in the process include prototyping, which entails assembling and testing components, and product making, which entails building the finished design. The system's performance is measured through data testing, and the efficacy and efficiency of the outcomes are assessed through data analysis.
For data number 1, the bar graph shows the lowest and highest voltage outputs of piezoelectric tiles in prototype 1 and 2. Increasing the number of tiles generally raises voltage output but may reduce efficiency at higher quantities. Prototype 1 peaked at 18.77 volts, 12 tiles, but dropped slightly with more tiles, while Prototype 2 peaked at 19.27 volts, 24 tiles before declining. This result suggests a trade-off between tile quantity and efficiency. Additionally, Prototype 1 can connect with Prototype 2 to improve energy generation, highlighting the potential for integrating multiple piezoelectric devices. For data number 2, the findings highlights the significant impact of pressure, strength, and pattern on the voltage output of the charging piezoelectric station. In Prototype 1, heavier steps resulted in more stable and higher voltage, 7.28 volts to 19.86 volts, while lighter steps produced lower outputs, 4.64 volts to 14.02 volts. A combination of steps led to fluctuating voltage, 8.59 volts to 15.37 volts, indicating irregular energy transmission. In Prototype 2, mild steps gradually increased voltage to 13.01 volts, while strong steps reached a peak of 18.94 volts. Mixed steps resulted in inconsistent volts, 4.99 volts to 11.21 volts, likely due to inefficient energy transfer. These results emphasize the need for consistent and uniform force application to optimize energy generation.
For the data number 3, the line graph compares the time required to charge iOS and Android devices by 1% at different battery levels. iOS charging times fluctuate significantly, ranging from 572 to 998 seconds with no clear pattern. Android devices exhibit more stable charging times, varying between 577 and 872 seconds. Overall, Android charges faster than iOS, except at 3% and 8%. The variation in charging speed may result from battery management systems that regulate charging to prevent overheating and extend battery lifespan.
So, for the conclusion, the study finds that increasing piezoelectric ceramic improves energy harvesting, though efficiency slightly declines beyond 30 pieces. Voltage output depends on pressure distribution, circuit resistance, and mechanical inconsistencies, with heavy steps producing more stable voltage than light or mixed loads. Android devices charge more reliably than iOS using a piezoelectric station, with both charging faster at higher battery levels. Future research should focus on improving voltage stability and efficiency for practical use in low-power devices like wearables and sensors.
Here are the references of the study. And for the acknowledgement, we extend our deepest gratitude to everyone who contributed to the success of this study. Our sincere appreciation goes to our teachers for their invaluable guidance and encouragement throughout the research process. We also thank our peers and mentors for their constructive feedback and support. Special thanks to our families and friends for their unwavering encouragement and motivation. Lastly, we acknowledge our school and New Nazareth University that provide the resources and assistance necessary to complete this work. Thank you all for your contribution and support.